Eric, you're on.
Great, thank you. I just wanted to check that my slides are visible.
Yep, it is.
Okay, great. Yes, thank you very much for organizing this, and it's an honor to have a few minutes to talk about this. I thought I would start by kind of orienting where my area of research falls on the sort of general map of computer science. Broadly speaking, I'm at the intersection of these different sub-areas of computer science: programming languages and formal verification and concurrency. And my interests are on ensuring that concurrent programs operate correctly and are able to exploit multi-core architectures. So let me step back a minute. Software reliability is a major problem that plagues us even more and more as time goes by. We're all aware of news events about how software has had catastrophic impacts when there are bugs in those pieces of software. And this Boeing is just, unfortunately, yet another example along a long history of software defects. And of course, as scientists and engineers, I think we all agree that software should be reliable, and we would wish that it would have really strong guarantees that come with it. So that's one issue. And then meanwhile, there's a somewhat competing issue, which is that there's often a need for speed in software computation, that we're able to get results quickly. That's important sometimes for security, sometimes for just practical purposes, sometimes for livelihood. And so we need to be able to very quickly also have reliable and quick computations. And meanwhile, there's been a fundamental shift in the architecture of multi-core systems. And so unfortunately, we're no longer seeing clock speeds increase the way they used to. And instead, the chips that we have now, perhaps on most of our laptops, are either dual core, quad core, or in servers, or often sort of multi or many core. And so that, from a programming languages perspective, and compilers, we tend to look for ask what are the new programming languages that programmers can use that would be able to better exploit that concurrency and do so reliably. So that kind of sets the scene for the types of challenges that interest me. I've sort of sketched here a few of the broad themes or projects that I've been working on, and I'll just kind of quickly talk about one or two of them. So in tackling this issue of programming models to support multi-core architectures, that means that we need some kind of method of concurrency. We need to be able to allow programming languages to emit code that can do multiple things at the same time. And it's long known that one way of tackling that, or a kind of abstraction to keep in mind for that, is a notion of commutativity. And so maybe I'll kind of extend this Formula One analogy. So a Formula One car comes into the pit, and it's really important to very quickly service this car and get it back out onto the track. And so in order to do that, what the crew leverages the concept of concurrency to do so quickly, right? They have all these different operations that need to be performed, and they try to do them all at once, or as much as possible, do them at once. So we can think of these as like different operations that are happening on this car. And some of those operations are independent of each other. So for example, the guy who's changing the rear wheel, his operation is completely independent of maybe the person who's changing the front wing. And we can think about that in terms of what we call commutativity. That is, that those operations could, logically speaking, happen in either order, because they don't really depend on each other, and either way they're going to have the same final results. And so that's really useful because it means that they can happen concurrently, because they have this independence. Of course, not everything is commutative. So if you think about the rear jack operator, right, that has to happen before the rear tire is removed. Right, because in one order that makes sense, and in the other order it's impossible to do. So carrying that analogy now down to programming languages and data structures, we similarly may want to have some sort of shared data structure like a hash table, and concurrently perform operations on that hash table. So maybe one thread that's running on one core may want to put an entry into the key X of a hash table, while another one may want to get an element from the hash table that's at some key Y. And so we want to ask these questions about what are these commutative operations? Can they happen in any order? Or if they're not in general, are there specific circumstances where they are commutative? So for example, with a hash table, assuming it's implemented in a certain way, if these keys are different, if X is distinct from Y, then logically speaking, they can happen concurrently because you'll have the same result regardless of the order that they happen. So this is really helpful because that means we can take programs that are written in a sequential way, where first the put happens and then the get happens, and incorporate other notions of what are called atomicity and linearizability to then transform the program into one where these operations can happen concurrently or in parallel. This is not really a new idea. There's a long history of knowing that commutativity enables parallelism. It goes back to the database community. And then back in the late 90s, there was work on parallelizing compilers that exploited commutativity to do that. And then about 10, 15 years ago, there was kind of another slew of papers that looked at exploiting commutativity for a wide variety of contexts. So transactional memory is one of them. Also runtime systems, also graph algorithms using commutativity to know what's independent there. And more broadly, a few years ago, there was a study from MIT that talked about how software scalability can come down to commutativity. So to point one point on there, we have a paper last year in Atlas that showed how commutativity can really speed up even software transactional memory, which is supposed to be a concurrent programming paradigm. So that's one sort of general direction that I've been working on, and we have some recent work that I was doing this past semester and a paper that's now under submission. And so what we've been doing in this work is we'll take a programmer's input, they've written some kind of collection of data structures, and then used a variety of techniques to analyze the implementation of those data structures using things like abstract interpretation, symbolic execution, symbolic analysis. And from that, we actually are able to generate a proof of the conditions under which different operations commute. So prove that under certain circumstances, the hash table operations will commute. So that's very useful because we can then use that proof inside a compiler in say the optimization phase to transform this sequential program into a concurrent version that has, it's sort of broken into pieces. And those pieces can happen concurrently. And that allows us to better take advantage of multi-core architectures. There are lots of research questions here, though this is really sort of early stage at this point. So we're interested in knowing, can we analyze existing programs like I've just been talking about and discover commutativity? So look at someone's program and see if that's can be discovered. And then can we employ that and observe speedups? And then more broadly, can we move beyond the programming languages that we have today and imagine new programming languages that are intimately connected with commutativity and allow for a lot more concurrency? So we have a couple projects going on in this domain. So recently I was fortunate to receive an award to support this type of research, which I have a PhD student that's going to be working on it and another one joining in the fall. There's a couple papers that that we've already done in this area. So one was from Takas a couple years ago. In my research, I also like to build prototype tools, verification tools. So we also have a collection of a couple different tools that we've been publishing. And then looking ahead, I'm interested in looking towards what programming languages are sort of more intimately connected to commutativity. And in this project, I just also wanted to show my support for this initiative. And part of this project is to try to bring some of these techniques or enable people to have kind of hands-on experiences with these techniques. And so I just wanted to use this opportunity to mention that if anyone is interested, I am trying to look to create some kind of hands-on event. It's not necessarily geared to this particular research or my particular research, but to try to reach out and bring people in order to learn more about research and get more involved. And of course, there are lots of challenges involved in doing that, especially in the context of coronavirus. So then one other topic of research that I'll briefly mention is this ONR supported project. So here we often have a circumstance where there's some computer program we've been working with for a while. Maybe everything is going mostly okay, and then some modification happens to it. A programmer makes a change, and now we have a new version of the program. And we're often wondering, well, what has been the impact of this change? Have we improved the program? Has this made things worse? Has it introduced a bug? How does the new program relate to the previous program? And this circumstance comes up even as a programmer, someone who's working with source code, or maybe even in the absence of source code. So you have some program that's running on your phone and you install an update and now you have a new program. And the question is, how do I relate this new program to the previous one? Is it one that I should trust, or are new bugs introduced? And this is the topic of our ONR supported AVTA project. And so this understanding the differences kind of sounds like a diff, and we've all, or many of us have probably used diff-based tools, like even GitHub offers a nice one. But we want to go beyond that and understand more semantic differences that occur as a result of changes. So there's a lot of research questions in this area as well, especially since we want to work with binaries. And so typically those binary decompilation techniques there's a collection of them available now, but they are really typically focused on enabling recompilation. And we're working to try to retarget them for verification or program analysis so that we can prove properties about these binaries. And there's a collection of questions that are there. We've made some progress on this project that's now been going on for a couple of years. We're fortunate to have Professor Jun Xu and David Nauman who have been contributing to this project as well. And some of the papers that have come from that listed here. Again, we also like to create tools and artifacts of the work. So a few of those are now available on GitHub or will soon be available. Moving forward in this direction of understanding the correctness of computer programs, we're also looking towards incorporating some dynamic analysis along with or in concert with static analysis. So we have some new work that's under submission there, and some interesting directions forward there. So that's just a sort of highlight. If any of this sounds interesting to anyone, I would love to hear, to have your feedback, your thoughts, and I'd love to look for opportunities for collaboration. So please feel free to reach out, and I look forward to hearing other talks. Thank you.
Okay, thanks very much, Eric. Very exciting work, and congratulations again on your recent NSF funding success.